Okay, so let's look at rates of change. So in the previous sections, this is kind of taken from your book anyway, but in the previous sections we've seen what a rate of change is. So the rate of change of a function, so y or f of x, depending on which notation we're using, is denoted by dy dx, or that f dash x that we saw before. So we said these two things have the same meaning, dy dx or f dash x, and how we introduced that at the very start of the chapter was as a rate of change. So it was how the function y changes with respect to x. That was what we were writing it out as. So we were looking at how does y change as x changes, and that was kind of described by that dy dx, with the d part technically represents that idea of change. So that word d, like the letter d, really is supposed to represent change, which is the change in y over the change in x. And these have practical applications which are really important, I suppose, for us when we're looking at the sort of questions that we could be asked. So the first one there obviously is looking at speed. So if an object moves in a straight line, the distance travelled, which is usually denoted by the letter s, depends on the time t. So for example, if the distance is given by this formula here, where s is equal to 3 minus 6t plus t cubed, then the rate of change of s is going to be ds dt. It's important here just to recognise that this letter s here doesn't represent speed, it represents distance, so slightly different from what we might think. Acceleration is another good example. Acceleration is how does speed change. So given that we already just saw that speed here is represented by this ds dt, acceleration goes a step further and says, okay, well, we know speed is the change in distance over time, but now acceleration is the change in speed over time. So that's going to be the rate of change of ds dt, which gives us the acceleration here. And we can see that that's represented by our second derivative. Yeah, let's make a note of that just so we remember. That's our second derivative. Okay, rate of change of area. So if we're given area by a particular equation, then we can check the rate of change of that, get dA dor, depending of course on what the variables are and what the letters involved are, these formulas will change. Same with the rate of change of volume, a common enough one. If you're filling up a container, volume would be given by one formula. It's usually dependent on time, and then the rate of change of the volume would be dv dt. So what we can see here is that idea of rate of change being related to, and this is what we had at the very start, that over that kind of d over d, that first derivative, okay, that derivative. So this idea that rate of change is related to dy dx, and we saw this when we introduced it. That's how we phrased it from the very start, was that slope and rate of change were related. We said slope was an example of rate of change. These are more examples then. So here we have a little bit more of a kind of standard definition, I suppose. So if y is f of x, dy dx is the rate of change of y with respect to s. And then they look at distance and acceleration as we did there. What we might want to make note of are just these kind of common ones here. Okay, and obviously we're hoping to understand it that little bit further, but it's worth just making note of these things as well, just to make sure that we know them as we move on. So to find the distance or the height at a time t, we sub into the original formula. Okay, standard enough. So generally that's what's given, distance or height would be given. To find speed or velocity, sometimes it would be called velocity instead of speed, we find the first derivative, so that would usually be ds dt, or if we're looking for height, so maybe the height that a rocket goes at, and then we're looking at what speed, that would be dh dt. So again, depends on the formula, but these are just the common ones that we might see, that we might need to just think of. To find acceleration, we're finding second derivative, because that's the change in speed over time. So it's the change in the first derivative. And then lastly, if we see a question that asks us for momentarily at rest, that's going to be where the first derivative is equal to 0. And thinking about what that means in terms of some of the examples we have here, we said the first derivative was speed. So we're essentially saying when it's at rest, the speed is 0. which makes sense. Okay, that would follow along that when it's momentarily at rest, the speed is 0. If we think of throwing something in the air, if we throw it up, it goes up, it goes up, it goes up, it goes up, and then it's going to start coming back down. But just before it starts coming back down, it's going to pause here, the very top. And that's what we would consider to be momentarily at rest, at that turning point. So again, we're back to turning point. We know dy dx is equal to 0. Okay, so we're making all these connections. And there's a lot that we've done in the last sections, and it can just be hard to keep it all straight. So it's just making sure that as we go through each section that we're really clear on what everything means before we move on to the next one. So let's look at an example. Water is being collected in a water tank. The volume of water in the tank after a particular time is given by this formula. Find the rate of change of volume with respect to time. So let's have a look at that. So keywords here, rate of change of volume with respect to time. Okay, what that means for us is we're going to be looking for how does the volume change with respect to time. Okay, so the first one, the rate of change of volume, that's your first variable, that's your dv. With respect to time, that's the dt then. So dv dt, we know what v is. dv dt, the 3t squared becomes 6t, the 4t becomes 4, and the 2 just goes away. Okay, because it is a constant, so it's just differentiated to nothing. Now we're asked to find this rate of change when t is equal to 2. So now we're going to have to take this value and sub it into our formula. So we're going to sub in the value of t is equal to 2, and we get 12 plus 4, and we get a value of 16. Now for this question we can look at what we've been given, and we were told that this is t minutes and v is cubic meters. So this 16 is actually meters cubed per minute. Okay, so it's the unit of the volume over the unit of the time, in the same way that we had our dv dt was a fraction of sorts with the volume on the top and the time on the bottom. So our units for this result is going to be the volume over the time, the units of the volume over the units of the time. Okay, let's look at another example. Okay, for this one we're going to have to cast our mind back to those common ones that I showed you earlier, the common derivatives and the common rates of change. So we have a body moving along a straight line. By a body they just mean some sort of object, and its distance s meters. Let's just make note of that. So distance is s meters from a fixed point after t seconds is given by this formula. It's a cubic formula, and we are asked to find its speed. So what we should remember from those notes that I had earlier, and if not, maybe take a second, scroll back up or look at your own notes, but speed is the rate of change of the distance with respect to time. It's the first derivative, so we're going to find ds dt for this first part. So let's try that. ds dt, and the 3t cubed becomes 9t squared, the minus 4t becomes minus 4, and that's our first part. Okay, that's our ds dt. Next we're asked to find its speed after 2 seconds. Okay, if we want to think about what that means, we're looking for ds dt, which is our speed, when t is equal to 2. Okay, and we should know generally if we're looking for a particular value of t, we sub that in. So we have ds dt over here on the right hand side, so I'm just going to rewrite it here, and I'm going to sub in t is equal to 2. So let me see, I'll use a different color here so we can make it clear. T is equal to 2. Okay, so we're subbing in for that value of t, minus 4, we get 9 by 4 minus 4, 36 minus 4, which is 32. And if we want to check, we're looking at speed, so it's meters per second, okay, from the question, meters per second. Okay, that's our second part. So again, making that connection, speed is the first derivative. If we start with distance, next we'll get speed. Okay, so our first derivative will be speed, so that's something we need to just file away. The third part here says after how many seconds the body is at rest. Okay, this is where we need to again think about earlier, what does it mean? What does it mean for it to be at rest? It means it's not moving. When will it not be moving? It won't be moving if, and we'll use the words, if speed is 0. If the speed is 0, it's not moving. And then if we remember, speed is ds dt, it's the first derivative. So we're looking for where's the first derivative equal to 0. So let's give that a go. We'll write that out for ourselves. That's where we get maybe our 1-2 marks at the start of the question for recognizing, okay, you're asking me to find when is ds dt equal to 0. Then I write out my question, I write out my formula. I write out ds dt. I put it equal to 0. What we need to recognize at this point, and let me move this down, is what this type of question is. And this is a difference of two squares. Okay, we said this in the last section, that if we have a question where we have a t squared or an x squared, we generally will have to do some sort of factorizing. And we kind of start with quadratics and we say that's not a quadratic, so the next would be a difference of two squares. So for a difference of two squares, the 9t squared can be rewritten as 3t. 3t all squared. And similarly, the 4 can be rewritten as just 2 all squared. Okay, and then for a difference of two squares, we end up with two brackets. The first one being 3t, so the first one is 3t minus 2, and the next one then is going to be 3t plus 2. And this is all equal to 0. If we have two brackets like this, or two factors equal to 0, now we need to split them up. So we say 3t minus 2 is equal to 0, t is equal to 2 over 3. 3t plus 2 is equal to 0, t is equal to minus 2 over 3. And obviously at this point then, because we're looking at time, and we think back to the question t represents time, we're going to go with the t is equal to 2 over 3 as our answer here, because we don't want to obviously have a negative time. The last part we need to look at then is part 4, and we're asked to find acceleration after 3 seconds. So again, we're throwing our mind back to those common ones that we looked at earlier. Acceleration is going to be the second derivative. Okay, the second derivative. So d2s dt squared. So to find our second derivative, we look back at the first derivative and we're going to differentiate that further. So my first derivative is up here, ds dt, it's 9t squared minus 4. I'm going to differentiate that further. That becomes 18t. The 9t squared becomes 18t. The minus 4 is a constant, so when we differentiate it, it goes to 0, just goes away. So we're left with the acceleration is 18t. So we see it depends on t. This is a general form. We've been asked when t is equal to 3. So we're going to sub that in. So 18 by 3. Okay, and if we multiply 18 by 3, what is our answer? Let's just try that one out. And we should get an answer of 54. 54. So 54 is our acceleration. Okay, so the key things there again are recognizing those common derivatives, those common rate of change, knowing that speed is the first derivative, acceleration is the second derivative. If the body's at rest, then the speed is 0. Remembering that again, speed is ds dt, so that means ds dt is equal to 0. And we can see what I've done even in this question is when I've recognized what the question's asking me, I've made note of that, I've written that in for myself. Particularly part 3 there, where I wrote down ds dt is equal to 0, and that again is showing an examiner in this situation, of course, that I know what I'm doing, that I know where I'm starting, and even if I can't go any further, I know that for it to be at rest, ds dt is equal to 0. Okay, so that's the idea. We will do one more example. This one we're looking at a rocket. So a rocket is fired vertically upwards, and after t seconds, its height, h meters, is given by this formula on the right hand side. Okay. So similar to the last one we had distance, this time we have height, but we saw that in those common ones that we were looking at. Okay, so we're given a height. We're asked to find the height of the rocket after 2 seconds. Okay, so let's just do that. So we take our formula for h, which is our height, and we want to do it when t is equal to 2. So let's just sub that value in for t. Becomes 2 squared here. And then we just follow that through. So 200 minus 5 by 4, 200 minus 20 becomes 180, and our height is meters. So 180 meters. So when t is equal to 2, the rocket is at 180 meters high. Okay, part 2 says velocity. And velocity, what we need to remember is that velocity is going to be the same or behave the same way as speed. And we've said that speed is ds dt, the first derivative. Velocity, again, is the first derivative. It's dh dt. You need to learn that off. Velocity is the first derivative. So dh dt. So finding dh dt, the 100t just becomes 100. The minus 5t becomes minus 10t. The minus 5t squared, becomes minus 10t. And that's our velocity. Now we've been asked to find the velocity when t is equal to 3. So we can sub that in. 100 minus 10 by 3, 100 minus 30, and we get 70. That's our velocity, so 70 meters per second. For the third part, we're asked to find after how many seconds. Okay, first of all, after how many seconds. So after how many seconds, we are looking for a time. Okay, so they've asked after how many seconds. We're looking for a value of t. The rocket is momentarily at rest. We should remember that momentarily at rest means speed is 0. So speed or velocity, same thing, speed is 0. So looking at that then, we want to know when is dh dt equal to 0. Okay, again, I'm writing that out, I'm making that clear for myself. And we've gotten that from those things that I've highlighted in pink. That's how we've come up with this. So I take my dh dt from the right hand side here, and that was 100 minus 10t. We're going to set that equal to 0. 100 is equal to 10t, which means t is equal to 10. So after 10 seconds, the rocket will be momentarily at rest. It'll stop for a second. The speed will be 0. Part 4 now says find the maximum height. The maximum height. And the maximum height should bring back to us the idea of turning points. Okay, so remember, at a maximum or a maximum turning point, what do we know? At a maximum turning point, dy dx is equal to 0. Okay, in this question we don't have dy dx, but we can still use the same idea. dh dt is equal to 0. The letters are different, but it's still the same. dh dt is equal to 0. Where is dh dt equal to 0? Well, that's when t is equal to 10. So what does that mean for us? At the maximum height, the time is 10. So when t is equal to 10, the rocket is at its maximum height, the turning point. It makes sense that it has to go up as high as it possibly can, and at that highest point is where the speed will stop and where your rocket will start to turn and go back down again. So we need to find height when t is equal to 10. And to do that, we're going to use our h formula that we had at the very start, remembering again what we had in that little cheat sheet, if you like, where we said if we're asked for height or distance, we're subbing back into the original formula. We are asked here for maximum height, but we're looking for height, so we're subbing back into the original formula. We're subbing in this value for t. T is equal to 10. Use the yellow here maybe. So t is equal to 10. So anywhere I see t, I'm going to sub in that value, that 10. And same over here, minus 5 by 10 squared. And we get 1000 minus 5 by 100, and following along, and we get 500 meters is our maximum height for this function. Okay, maximum we're going to look at a little bit more in the next section, but for this section the main things to be aware of are these idea of the rates of change, and we can see here in those three examples we've really approached them all the same way. We're asked for a lot of the same things. So looking at this sheet here, this idea, so if we're asked for distance or height, we're going with the original formula. For speed or velocity, it's the first derivative. For acceleration, it's the second derivative. Keeping those ideas in mind is going to be really important for these sorts of questions. Okay, the idea of rate of change, so how does it change with respect to another variable? And then tying in those ideas from the previous section. So how do I find a turning point? How do I find a maximum turning point? How do I check if it's a maximum turning point? These things are all going to be really important. So this is why it's important to have those previous sections really clear and being really confident with those so that you can use them then for these sorts of questions. Okay, but stick with it. Okay, identify what you're looking for and then try your best to move towards that.